Yeah. Um, so welcome to class 5, and we continue from where we stopped yesterday, the last class, and we're going to discuss entropy, properties of entropy. Uh, what is the meaning of entropy? What is the meaning of some quantity called the free energy? And we're going to calculate these quantities in various ensembles and various contexts. The statistical physics when we start actually statistical physics, and some of the quantities that we calculate in statistical physics, we are going to call them uh, entropy and free energy because they have the right properties, and we're going to use the properties that we define today in for entropy, free energy, Helmholtz free energy, and so on and so forth, to make a correspondence between the quantities that we calculate in statistical physics, and also take their suitable thermodynamic derivatives, which we're going to discuss today very briefly. And we're going to use those relations once we have found the mapping between the quantities that we calculate in statistical physics and entropy and free energy under different contexts. Right. But those quantities that we shall calculate in statistical physics will be calculated in terms of microscopic variables, and statistical physics will also give us a quantitative measure of the fluctuations, which is completely missing in our current discussion of thermodynamics, where we are describing all the processes in terms of macroscopic state variables. So before we start today's class, I will just quickly go through one point. We discussed this problem at the end of the last class. And here you see that the efficiency is again 1 minus T1 by T2, which is very reminiscent of the Carnot efficiency. Yeah? But there are differences, and I want to point out those differences even as we, though the formula looks the same. So in the Carnot cycle, when heat was absorbed or released in a reversible manner, the reservoirs from which heat was extracted was at fixed temperatures T1 and T2. And correspondingly, the amount of heat which was extracted or given back to a reservoir at T2 and T1, T2 being the higher temperature. So when those were, so in the Carnot cycle, these reservoirs were at fixed temperatures even as heat was gradually extracted, and as a consequence, the heat extracted in a reversible process was directly proportional to T2 in one case in the higher isothermal process, and equal to T1 in the proportional to T1 in the lower in the isothermal process at the lower temperature. However, note that when heat is being absorbed here, the temperature itself of the system is changing gradually. So this is not an isothermal process. And if we have to do this reversibly in a quasi-static manner, the temperature of the heat path itself has to change gradually. Right? So in this process where heat is absorbed, it's not an isothermal process. Temperature is changing from T2 to T3. Right? And similarly here, this is an isochoric process. The volume remains constant and heat is given out. As a consequence, the temperature itself changes from T4 to T1. So in general, when we write it, the efficiency is actually T4 minus T1 and T3 minus T2. But of course, then we use other relations, thermodynamic relations or equations of state to get it in terms of T2 and T1, the efficiency. But though the formula remains the same, meaning is quite different. And these are not isothermal processes. With that, let's begin new topics. What you have already seen is TdS, which is the heat absorbed, but that's the heat absorbed only if the process is reversible and not otherwise. TdS is not equal to the heat absorbed. TdS is going to be greater than the heat absorbed for a non-reversible process. But for a reversible process, this TdS equal to du plus pdv, where TdS is equal to dq holds. And this holds for a closed system. That means that the system can exchange energy, but no particle exchange is allowed, right? And that is different from an isolated system, because just to remind you, an isolated system, neither heat exchange was allowed, nor a particle exchange was allowed. So a system, an isolated system would relax to equilibrium if it was not already in equilibrium. And once it reaches equilibrium, it will stay there. And as we shall see that for an isolated system, equilibrium will be reached when the entropy is maximum. But before that, what's the meaning of entropy? So before we go on, so du was the internal energy. It was as a function of state, as realized experimentally. Okay. The other thing I would like to say that for a gas, right, when you do work, I mean, it was seen for an ideal gas, du was only a function of temperature. In general, for a gas, du will be a function of density as well with an interacting gas, right? But if it's sufficiently dilute, then and I mean, in close to the non-interacting limit, even if it's interacting over the scale of work which is done and which leads to volume change, the contribution from the potential energy can be quite minimal. It need not be minimal, but it can be minimal. But anyway, for most of the purposes that we are talking about, we are talking about obtaining work from an ideal gas, in many cases, not always. And on the other hand, if you had a solid or it had a liquid, the amount, significant change in the volume would really have, I mean, you have to give enormous amount of pressure to change, suppose the volume of a liquid or the volume of a solid, right? But anyway, in general, du equal to dq minus pdv holds, and this minus pdv means, so in the way it is written, that the system itself is doing work on the surroundings, right? So on the other hand, if work is done on the system, then its internal energy would change. So that would be decided by the sign of dV. dV can be, volume can increase or decrease, right? So in general, so we have also talked about this experiment where where work is done and you rotate suppose a fan, and it's a adiabatic wall, all the work can be converted into heat. The temperature would be raised, right? And but in general, TdS, if it's the phenomena, if the process which we are discussing is irreversible, TdS is not equal to the heat gained or lost by the system. TdS can be greater than or will be in an irreversible process, it will be greater than the heat gained or by the system. Okay. So why and how? Let's discuss that. So for an irreversible process, I'm saying that TdS will be greater than the heat gained or lost by the system. Just let's discuss this for some more time to understand what this means. So this relation also means that for the small quasi-static process going from A to B, SB, the entropy. So we defined entropy to be dq by t, and it was a state function, and differences can be calculated if we take a path, a reversible path, right? Because entropy is a function of state. So SB minus SA, is taking the t this time in this side of the equation, can be greater than going from A to B dq by t, right? And the equality holds only for reversible processes. That's how you can calculate difference in entropy in going from A to B. If you take along, if you calculate along a reversible path, but in general, this TdS can be greater than dq. So the question which might be in your mind is ds was defined in a reversible process. Now, how come this ds greater than 0 in a process coming, right? So in an irreversible process, there will be some entropy which will be generated. So where here this ds here, so here it is a system which is going from A to B, but this ds greater than 0, when I mentioned the ds greater than 0, here what is implied is the entropy of the system plus the universe. Because in a reversible process, whatever entropy is gained or say lost by a system, equal an amount of entropy is gained by the reservoir, right? Because in the reversible process, this is the equality holds, an equal amount of heat is absorbed by the reservoir, and the total, the sum of dq by t of the entire system remains equal to 0 if it goes from A to B, right? Whereas if it comes back in a cyclic process, if it goes from A to B and from B to A, comes back, and then this entire process is reversible, then the amount, so if you just look at the system, like q1 by t1 plus q2 by t2 will be equal to 0, because it has come back to its original state, and the reservoir also has not created any entropy. However, in an irreversible process, the sum of the entropy lost and the entropy gained by the universe, the sum is not equal to 0. Instead, some entropy is created. ds is greater than 0. And the question is, how does this come in? And it comes from the idea that the Carnot engine is the most efficient engine between two temperatures, which is a consequence of the second law of thermodynamics, right? So if this was your system or the engine, if you like, so Q2 was being absorbed at temperature T2, and it was again released in a Carnot system, and this was adiabatic. And heat was again released. Q1 was being released at temperature T1, right? And in the Carnot cycle, there was this proportionality between Q2 and T2 and Q1 and T1, and this relationship holds. So the ratio of Q2 by Q1 is equal to T2 by T1, and efficiency was defined as 1 minus, work done, which is Q2 minus Q1 by Q2, or which can also be written as 1 minus Q1 by Q2. And this was shown to be 1 minus Q1 by T2. Right. Now, Q1C, this Q1C was the heat given out in a Carnot engine. So that's your system. And that is giving out an heat Q1C. And Q2 again was the amount of heat absorbed by the engine. Now, if there was dissipation, if it was an irreversible process, if these were not idealized, these were not reversible processes, as it happens in reality, right? So even as something would move and this system would absorb some heat, so what you would have is Q2 would be the heat absorbed by the engine, because we are focusing on the engine right now. So how much heat it absorbs, but the amount of heat which would be given out by the reservoir might be something more. It might be Q2 plus Q2 dash, and that's lost due to dissipation or irreversible processes to the universe, to the reservoirs. So that part is given out to the reservoir. But from the perspective of the system, it absorbs heat only Q2. However, when it gives out heat, and that itself could also be an irreversible process, and some due to friction, some heat would be lost, then this system would give out Q1 heat. That's the energy lost by the engine, some of which it would give to reservoir, let's say Q1 dash, and some of it might be dissipated. Let's put it as Q1 double dash. Now, if it was reversible, this process was also reversible, then Q1 would be equal to Q1 dash, because there's nothing which is heat which is dissipated, right? So for reversible cases, Q1 would be equal to Q1 dash. Yeah. And this Q1, and if this engine loses heat, Q1, right? If it lost this much heat, then Q1 dash would be zero in irreversible process, and this Q1 dash which is lost, which was dissipated, that would also be converted into work. But in this case, if it's an irreversible case, Q1 is being released, is being given out, right? But Q2 minus Q1 is not the amount of work done. The amount of work done is less, because some of it is being dissipated. This amount in an irreversible process, some of it is being dissipated as Q1 double dash, and the reservoir just gets only this much heat. So Q1 double dash by T1, Q1 double dash is essentially the entropy generated, and that is equal to the heat lost, which could not be converted into work. So the amount of entropy generation is related to, so entropy generation, system plus universe, is equivalent to the work lost due to irreversible processes, because it could not be converted into work. Yeah. So if there are some spontaneous processes for a closed system for which entropy increases, that again means some amount of heat is lost, and it's not convertible into work because some entropy generation has taken place, and that's the amount of work which is lost. So in general, what I want to say, that the Q1 in an irreversible process, the heat generated or dissipated, the given out by the system, let's take Q1 to be the amount of heat given out by the system, is more than the Q1 in a reversible process. Why? Because some amount of heat is being given to the reservoir, but some amount of heat is also being lost it's going to be dissipated, right? So the amount of work that the system is able to get on absorbing Q2. So this amount of heat the system is absorbing, some even as it absorbs, some amount of heat might be lost. But that's a consequence. That's some entropy generated which we're not considering because it's gone to the reservoir. But if it absorbs Q2 amount of heat and gives out or generates Q1 irreversible amount of heat, then the amount of work done is Q2 minus Q1 irreversible, right? And that's a smaller quantity than Q2 minus Q1 reversible, because this quantity is more than Q1 reversible. So this is the primary amount, and that's what it means that entropy generation. So this excess, what has been generated in irreversible process beyond Q1 reversible by T, Q1 reversible by T, if it had given out just that amount of heat, no entropy would have been generated for the system plus the universe. But you see that more has been given out and less has been converted into work. So that amount has been the entropy generated, and that's the amount of work lost. So that's the primary idea I want to give you. And hence Q2 by Q1 minus Q irreversible. This I stands for irreversible, and here again I am highlighting irreversible by T1 is less than, because this quantity is more and it comes with a negative sign, hence so is less than Q2 by T2 into Q1 reversible by T1. So here again I have highlighted reversible. Now this and this on both sides of the equation are the same, but this comes with a both comes with a negative sign, and this quantity is larger than Q1R, and hence this is smaller on this side. Now this quantity is equal to 0 for a reversible process, right? This is 0 for a reversible process, and hence what you get is Q2 by T2 into Q1 by T1 non-Carnot or irreversible is less than 0, because this quantity would be 0, because this quantity for Carnot, I mean for reversible, this is equal to 0. Hence, this quantity is less than 0, right? So here, of course, Q2, Q1, the signs are Q2 is a positive number, Q1 is a positive number. So what I highlight here, that this amount of heat is more, but this amount of work got in an irreversible process is less than the work obtained in a reversible process, right? So in some sense, this Carnot engine gives a upper limit to the amount of work that can be extracted in such a process. So the corollary is that the entropy of a thermally isolated system never decreases, because if there's no heat exchange, right? So in a thermally isolated system, basically what you have here is, where is the thermally isolated system? So now if there's no energy exchange, so from somewhere you get entropy minus this quantity is always negative, but suppose there's no exchange, any spontaneous process, entropy always increases, especially if it's an isolated system, and that you can get because, yes, because any reversible process, suppose there's no heat exchange, but some process is happening so that it's irreversible. it's happening spontaneously. So the system is in a certain place, no energy change is being allowed, but suppose the system is non-equilibrium and some spontaneous change is happening in an irreversible manner. There is some heat is supposed not allowing heat to, but it's an isolated system, but the system is going spontaneously towards a certain direction in an irreversible manner because it's happening spontaneously. And that would be, if it's irreversible, entropies are going to always increase. So that's the meaning. So, yeah, so I think this, whatever I told, that has been explained in a greater detail here. Any reversible cycle can be decomposed into a set of many Carnot cycles working at different temperatures. Yeah, but if any one of them, yeah, so if there was any cycle, I mean, not only talking about Carnot, but talking of any cycle, it can be decomposed into a set of many Carnot cycles working at different temperatures. And even if one of them is irreversible, then this sum over all these small Carnot cycles, uh, if one of the processes is irreversible, then the sum of this Qi, Ti acting at different temperatures, the sum will be less than 0. And if it is every Carnot cycle, if the entire cycle was reversible, so that the sum of all the Carnot cycles were happening in a reversible manner, then the sum over I, Qi, Ti would be exactly equal to 0. So remember that the changes in entropy is defined over a reversible path only. So, when you calculate dq by t, it has to be equal to 0. So you have to choose a path. You have to choose a path in a reversible manner, and that's a state function because we proved it in the uh, previous class. But if we go by an irreversible path and return by a reversible path, then this sum will be negative or smaller. So if one of the steps was irreversible and this was basically okay, so here we had not returned, so you're just going from A to B, so you have just half of the process, and one of the and it is you are going through an irreversible process, then this will be smaller than going from A to B, and that is, and if you go over a reversible path, that's the entropy at state B minus entropy at state A. Right. So whatever I said, so this is for irreversible process, dq is less than T into SB minus SC, assuming the temperature is remaining constant. So I already explained these ideas. Thereafter, let's go to the idea of thermodynamic potential. So basically for entropy, if it was an isolated system, any spontaneous process would be an irreversible process, and that would lead to an increase in entropy. But the cases where a system is not isolated, it can exchange energy with its reservoir or its surrounding. And there, if there is a spontaneous process, we shall show that some other quantity called the Helmholtz free energy, that is the quantity which will be minimized. Entropy was being maximized in any spontaneous process. It would go on increasing in any spontaneous process till it reaches its maximum. On the other hand, if a system is interacting it's interacting by heat exchange, there can be exchange of heat with the reservoir, then the system will spontaneously move and volume is kept constant. It will we'll see that the thermodynamic potential Helmholtz free energy is the quantity which will be minimized till it, and then it will reach equilibrium. So to discuss thermodynamic potentials, let me remind you that for a mechanical system, if kinetic energy is equal to 0, And so the system will settle down to a position of minimum potential energy. I mean, you drop a ball and once kinetic energy is dissipated, it remains at the position on the floor where the potential energy is minimum. But of course, if there's kinetic energy, the ball is going to keep jumping up, and there will be conversion from kinetic energy to potential energy, and so on and so forth, right? So mechanical equilibrium, if there is no motion, the equilibrium will be reached when potential energy is minimum. But what about the thermodynamic system? So in a thermodynamic system, the system can take heat or release heat from its reservoir. So you also have heat and work. And suppose T and V were fixed. So then, as I said already, Helmholtz free energy is minimized in an isothermal and isochoric process. Right. So here we have again written down TdS equal to du plus dw, work done. And of course, you can write TdS equal to the heat absorbed or absorbed only for a reversible transformation. So this is in contact with heat bath at constant temperature T. One assumes the system can exchange energy, but only with a heat bath at constant temperature T. And I've already mentioned that the heat absorbed or released will be less than TdS for an irreversible process. So here I'm writing it slightly differently. I'm rearranging the terms. So the work done equal to minus du plus dq for a reversible process, right? On the other hand, dw, the work done, is less than equal to minus du plus TdS. So note TdS equal to TdS equal to dq only for reversible process. Here I've written TdS, which is more than dq. Hence, the work done will be less than minus delta U plus TdS for an irreversible process or spontaneous process. So the equality, if there's no work done, okay, so the equality, no, it's not no work done. So the work, so in a reversible process, dw equal to this. So this quantity, it gives the maximum for a reversible process. It gives the upper limit on the amount of work that can be extracted on transformation from A to B. Okay. So if there is some transformation from A to B, the work is extracted in a reversible manner. So this quantity is the maximum amount of work done as it goes from A to B. Now, in an isothermal process, and I shall tell you where we use isothermal. So this can be written as UB minus UA, and this is written as a fixed temperature T SB minus SA, right? So you have just stated it as a function, state function SB minus SA and valid for fixed T. And now UB, now if you define FB to be UB minus T SB and similarly FA to be UA minus TSA, then one can write this quantity to be FB minus FA, where F is F equal to U minus TS, which is the free energy, the Helmholtz free energy, right? So this relation can be written as dW, the work done, is less than equal to minus dF. So in a reversible process, the maximum amount of work done in an isothermal process, the possible amount of work done in an isothermal process is the change in free energy. So that's its meaning. So dF is the maximum work obtainable in an isothermal process, right? So, and now we have written this, and this was an isothermal process. There was heat exchange T SB minus SA. If it's reversible, this is the amount of heat exchanged. And however, if there was no work done in an isothermal and isochoric process, if there was an isochoric process, then dW would be equal to 0. Then you would get 0 equal to dF, right? Or, so the system moved from A to B, and hence you got minus dF. Now, if you absorb the minus sign, you'll get FB is less than FA. Like, if there was any spontaneous process which was going on, which was irreversible, in the presence of heat exchange, but no work done, and it was isothermal, then the system will go on. I mean, it will keep on evolving, and free energy will keep on decreasing till the system has reached its minimal free energy, and it has gone to a position that free energy cannot decrease further, because any spontaneous process will lead to a decrease in free energy. If it has reached its free energy minima, then the process cannot go on. It will stop. The spontaneous process will stop. And that's when the system would have reached equilibrium. Okay. Similarly, so that was Helmholtz free energy. And you interpreted it, I mean, a spontaneous process, isothermal, constantly, isochoric, constantly, no work done. And the system will keep on evolving till it reaches its free energy minima. Now, if you had a system, okay, yeah. So, so I've just repeated this. System will reach equilibrium in a spontaneous process, and it will keep on decreasing. Free energy will keep on decreasing till it reaches its minima. So, any process spontaneous with fixed V but heat exchange will go on till, and F will keep on decreasing till it reaches its minima, and then it will be its equilibrium state. I'm going to use this idea. In a canonical ensemble, we actually calculate the partition function, and from which we, and the log of it, we relate to the free energy. Now, so what we defined is the free energy equal to U minus TS. And so U is a function of state, is a state function. T is a parameter. It characterizes the system, and S is also a function of state. So F is a function of state. Now, dF, you can write it as du minus TdS minus S dt. We're just taking a derivative. And this in turn, du minus TdS, we are writing in terms of PdV. Why are we writing it in terms of PdV? Because if we change volume or if we change temperature, then F changes, right? Now, I mean, even if it had reached equilibrium and now you change its volume or you change its temperature, so F would have reached its minima at constant volume and constant temperature. Now it is already at an equilibrium. It has reached its minima. Now you're changing its an external parameter, which is volume or temperature, and that will lead to a change in F. So F is a function essentially of V and T, and of course the total number of particles, needless to say. So if you take, so these are the, so F is a function of V and T, and if you take the derivative of, partial derivative of F with respect to V, you get a minus P at constant temperature, right? And if you take a constant derivative, if you take a partial derivative or with respect to T at constant volume, so this should have been volume, so this is wrong, at constant volume, then you would get entropy. So that is how, so in this case, you know, a system which is in thermodynamic contact, the quantity the system reaches equilibrium when F is minimized. And then by taking suitable derivatives with respect to T, you get your entropy value for the system, and a suitable derivative with respect to V, you get your pressure value, right? Furthermore, you can rewrite this function in a different way. And if you knew u, then a suitable derivative with respect to s, suppose you knew s, right? The internal energy you knew and you calculate your s from here, that would give you t. And suitable derivative of the internal energy with respect to v would give you p. And the reason I'm writing these down is because we are going to use these quantities. We're going to use these in statistical mechanics to calculate various quantities like Tp once we have made a correspondence about between different quantities. So that's why we are going through all of this. So yeah, and yeah. So you can also take a suitable derivative of S with respect to U at constant volume, and that would give you T, 1 by T, and so on and so forth. So it's basically this same relationship. And we're going to use these. You have also another variable called the Gibbs free energy, which is particularly useful when you are looking at transformations at constant pressure. So the previous case was at constant volume, but if you're looking at constant pressure, the thing to look at, it gives free energy. I'm not doing the derivation, but G equal to F plus PV. So F was U minus TS plus PV. Now, if you take dG, then you take du TdS minus SDT. So this gives minus TdS minus SDT. This gives plus PdV plus VdP. But then if you combine this, and this, right? So you get this quantity, and that if for reversible transformations, this plus this will be equal to 0. So what you have is minus SDT plus VdP, where the control variables you are working at really fixed temperature and fixed pressure. So if you have system at closed system, which means number of particles are constant, and you allow volume to fluctuate, but you maintain a certain pressure and a fixed temperature, and heat is allowed to exchange, you can show that in a spontaneous process, G is minimized if N, P, and P are kept fixed. F, when we are discussing F, N, P, and V were kept fixed. But in this case, G is minimized, so the system keeps on changing spontaneously. If you keep NT and P fixed, if you allow energy exchange, right? So it will reach its equilibrium when G is minimized. So there are other quantities like enthalpy and so on and so forth. They can be useful for thermodynamic purposes, but typically physicists deal with F, G, and S, especially in statistical physics. So the enthalpy and some other topics, I shall keep it as a side additional lecture. But we'll see whether we have time to discuss this in class and so on and so forth. So here I will stop this recording for this moment. We'll have a bit more of Maxwell's relations to discuss, which we'll be also using in the StatMech. So we'll also discuss that in brief and keep it in a separate lecture. And yeah, we'll see. So I hope I've stopped